Concavity and points of inflection are from the second derivative. So concavity is our first definition, and points of inflection. So concavity comes from the second derivative. The important part here is that the second derivative is either going to be greater than 0, so positive, or less than 0 and negative. If the second derivative is positive, then it's concave up. So the function is concave up. So this is the important part, concave up, if the second derivative is greater than 0. If it's less than 0, it's concave down. So concave up is up like a cup. So like a cup, so I usually say concave up is like a cup, which means it looks like this. So that's concave up like a cup. Okay? Concave down is like a frown. Ha. Okay, down like a frown, so it looks like this. So up like a cup or down like a frown. Now, for the up like a cup, it doesn't mean that it's always going to be the full cup. It could be half the cup, so it could be just concave up like that, or concave up like this. Okay, so it's not necessarily a full cup. It could be either side of it. Okay, same with concave down. It could be a partial frown like a sideways frown, or this frown like this, so sideways. Okay, so it doesn't mean it's the whole thing. Okay, so concave up is this, and concave down is this. So if it's greater, if the second derivative is greater than 0, it's concave up. If the second derivative is less than 0, it's concave down. Now, a couple things to note down. For concave up, they're saying that the slopes are increasing. So that means if you're taking your slopes or your tangents. Now, automatically, there's two things they want you to understand here or kind of point out here. Automatically, when you are drawing your tangents, where do you automatically draw your tangent for something that's concave up? You're going to draw it below. Right? There's no way I'm going to try to draw it above. That makes no sense. So automatically, even if it's just half, it's going to be below. So that's what the second part of the statement says. It says, the graph of the function is above the tangent at every point on the interval. So that means, I'll highlight that, the graph of the function is above the tangent at every point on the interval. So they said, oh, that's so cool, because anything that's concave up, when I draw the tangent, the function has to be above it, right? Even if I draw it here, no matter where I draw it, the tangent's always above. The function's always above my tangent line. The other thing they noticed is that the tangent line, if for the slopes of the tangents, they're increasing. So here the slope is very negative, then it becomes more positive as it's twirling around, right? So it's going around and you go, okay, it's more positive. Here, it is very negative, right? So it's a steeper slope, and then as you turn here, it's still negative, but it's less steep. So it's still increasing. So they consider that increasing. Here, it's positive, but as you go along the graph to the right, it's becoming more positive, a bigger number, bigger, higher slope. So they said, oh, look, it's increasing. So it's going from negative to less negative to positive, or from negative to less negative, or from positive to a bigger positive, higher slope. The function is always above the tangent line, right? There's no way I could try to draw the tangent line above it. So the opposite is true here. If I have concave down, automatically, where am I drawing my tangent line? Above the function. So it's above the function, right? Above the function, no matter where I draw it. And what's happening to my tangent line is that it's going from positive and then negative. So decreasing. Here, it's positive to less positive, right? So it's decreasing. So they consider the tangent line to be decreasing, and it's always above. Make sense? So as we draw our tangent lines, we can see our tangent lines are always going to be above. And then as we sleep here, it'll be more negative. Okay, so no matter what, we know that the function is always below the tangent lines if it's concave down and above the tangent lines if it's concave up. Just something interesting. Sometimes they'll say, instead of what's the concavity, they'll say, hey, is the tangent line above or below the function? And you'll be like, okay, if I know it's concave up, then I know the tangent line must be below the function. Or you could ask backwards and say, if it's concave up, is the function above or below the tangent line? So when they ask something about the tangent line, I draw it. And I go, okay, concave up means the tangent line is below, which means the function is above. If they say it's concave down, then I know, okay, concave down means the tangent line is above it, which means the function's below and is becoming more negative. Right? So anything they ask about the tangent lines, I usually draw it, and so you can kind of picture what they're asking. Right? So they won't always say, is it concave up or concave down? They'll say, is the tangent line below it? And you're like, you mean is it concave up? Yeah, it's concave up because the tangent line's below. Right? So it's just a backwards way of saying, is it concave up or concave down? But the first conclusion we want is concave up. So here, I know it's concave up for all of these. So concave up like a cup. And these ones here are concave down like a frown. Okay, and we'll use CU for concave up and CD for concave down. Okay, so the first thing I do is picture, is it concave up, concave down, and then everything else you can answer from there. All right, good with that? All right, the second part is, so that's concavity. So concavity, concave up, concave down, we understand that. The second part here is points of inflection. So in 4.4, we're looking at not just concavity, but a point of inflection. We will use this short form. So point of inflection, we're going to use POI. Okay, so POI is point of inflection. So point of inflection is here, where we have a point of inflection, is when the second derivative, right, so all this concavity stuff and points of inflection comes from second derivative, has to change sign. So it has to go from concave up to concave down, or from concave down to concave up. Okay, so on the number line, we're looking for a change in concavity. So if I get on the number line that it changes from concave up to concave down, that is not enough information. It's only part of the information, because if I know it's concave up to concave down, that means I could draw concave up like this, and then concave down like this. And this point here, I'll put arrows because I'm assuming the function will keep going somewhere. So that's concave up and concave down. So that's definitely concave up, and that's definitely concave down, correct? Then when it changes, this point here at the point where it changes, that is a point of inflection. We'll use POI to stand for point of inflection. But without the increase-decrease, I could have drawn this backwards. So I could have drawn it. So this graph here is telling me that it's increasing, right? What if it was decreasing concave down and decreasing concave up in your point of inflection? So this is still concave. Oops, sorry. Drew it wrong. So I want concave up. I want concave up, and then concave down. But it's decreasing. So both of those are satisfying the concave up, concave down, but I don't know what's happening unless I know if it's an increasing graph or a decreasing graph. So this goes from concave up to concave down. So this part here, sorry, I'm just going to circle this. So this is concave up, and that's concave down. This is concave down to concave up. So this part here is saying concave up to point of inflection here and concave down. So what's missing is that I need first derivative to tell me if it's increasing, or decreasing. Then I'll know which way to face it, because otherwise I only have concavity. So concavity alone is not enough to graph something. In your homework in 4.4, some of the question will say, use only second derivative to graph it. It's not enough, Okay, we will never ask you to only use the second derivative. For your homework, they're asking you to. I still throw in first derivative. Okay, when we ask you, it'll always let you use the first derivative and second derivative. This is not enough information. Concavity is simply not enough. Okay, so we will never make you just do one. I actually just do the first and second. Okay, so we'll do some practice ones with that. So again, the opposite would be concave down, so this is 2, right? So this is my second one. Let's draw one that's concave down to concave up. Okay, concave down would be concave down like that to concave up like that with a point of inflection in between. Make sense? Okay. But we don't know which way it's decreasing or if it's increasing. So concave down would be like this. And then concave up would be like this. Does that make sense? So we just don't have enough information. So concavity is not enough information. So yes, when it changes, that's a point of inflection. But we don't know what's happening, do we? Right? Not enough information. Second derivative simply does not have enough information. Okay, so concave down to concave up, concave down to concave up, but not enough information to know which one of the two. So you have a 50-50 chance of whether or not it's right or wrong. Okay, so now, second part. All points of inflection must occur. Do I need to label concave down, concave up? Are you okay with that? Okay, makes sense? It matches that. Okay, so all points of inflection must occur where either the second derivative equals 0 or does not exist. So equals 0 or does not exist or undefined means, so the fancy way of them saying is the points of inflection have to be, okay, and all they're saying here is numerator equals 0, right? That equals 0. And then here does not exist means denominator equals 0. Does that make sense? So their fancy way of saying either it equals 0 from the numerator or does not exist, which means you got the 0 from the denominator. If it's a vertical asymptote, it can't be a point of inflection because it's not a point, right? Vertical asymptotes already, the graph simply does not exist. That's restricted by the domain. Okay, so that asymptote is not a point of inflection. It's not a critical point. It's nothing, right? It's just an asymptote. Okay, so you either get it from the denominator. So we're going to do the equals 0 numerator, equals 0 denominator thing again. Okay, but, there's a but here. But just because the second derivative equals 0 does not mean it's a point of inflection. I'm going to underline that. Just because it equals 0 does not mean it's a point of inflection. So just because we get a 0 on the second derivative does not mean it's a point of inflection. How do we know if it's a point of inflection? Yep.
If it switches from up to down and down to up.
Exactly. You have to see if it switches. It goes from up to down or down to up. If it doesn't switch, it's neither. It's not neither. It's not a point of inflection. It's just nothing. Okay, it's not, and it's not a critical point. Our critical points still are coming from our first derivative. So our first, do you see any word of critical point here? Nothing, right? No critical point mentioned here. Critical points only come from first derivative, only from first derivative. Second derivative is getting us possible points of inflection, but not necessarily. Question, yes?
So when you say like up to down, is that positive to negative?
Yes, so it'll go from concave up, which would be positive, second derivative, concave down will be negative, or down negative to positive, yes. Right, so it'll switch signs. Good? We good so far? We're going to do more explanation, I think, on the next page. Yeah.